Assalamualaikum everyone. I hope all of you will be fine and you must watch the previous lecture, the previous lesson, which is about the electric flux and electric flux to the closed surface. If there is any confusion regarding that topic, so you can communicate with me, right, on my personal number and even in the group, and also you can communicate with me in the via Zoom, right? Okay, so today before going to start my current topic, which is about the electric flux to the closed surface, I would like to revise the previous knowledge, which is about the definition of electric flux and their various cases. Okay, so electric flux is nothing. Electric flux is just the measurement of electric field lines rho. Electric flux is the measurement of electric field line across any surface area, right? This is what we call electric flux. And mathematically we have defined electric flux as a dot product of electric field and vector area, and we have already discussed about the vector area as well, why in this case we consider a vector area, right? So this definition will be applicable under specific conditions. This definition is applicable only for specific circumstances. I mean, here the electric field must be constant, must be uniform, and similarly the vector area across which we are going to measure the electric field lines, it must be a flat surface. Then this equation is applicable, which is equal to E dot dA, right? Now I am going to discuss the electric flux through the closed surface. So before going to start to say about the electric flux to the closed surface, I would like to discuss what is meant by closed surface. Closed surface means any surface which bounds some volume, right? For example, if you have a ball, a spherical ball, if you have, so which bounds some volume, so it is considered as a closed surface, right? Or if you consider a room, right? So they have a six-sided sides, so it also bounds some volume. So this is also a closed surface. लेकिन उसके जो sides है, that is called a flat surface, right? So whenever I am talking about a closed surface, so this implies that it must be the object which bounds some volume, right? So now I am going to consider the electric flux to the closed surface. So here look at the figure 11.12. This represents one of the spherical object which is a closed surface, which is a closed which bounds some volume. But look at the surface of that closed sphere, which is not a flat surface, which is a curved surface, right? So here their area is not flat. Similarly, if we consider the electric field at any point over that surface, which is also not uniform. So the question is that how would you find out the electric flux to the closed surface, right? So before going to apply the definition of electric flux, as we have already discussed in the previous lecture, we have made some assumption, right? And on the basis of that assumption, we will be able to find out the electric flux to the closed surface. The first assumption is that we have to divide this closed surface into small segment, right, in such a way that the area of each segment is a flat. Each segment must be a flat surface, right, and the electric field across each plate must be uniform, right. So on the basis of these two assumptions, I am able to find out the electric flux to the closed surface, right. I mean, after that supposition, we will be able to apply the definition of electric flux as we have already discussed in the previous lecture, which is equal to E dot A. So in that equation, electric field and vector area, electric field is uniform and vector area is having flat surface. So under that supposition, look at this figure 11.12, and where we have zoomed one of the segment represented by a blue color, right. So we have divided all the closed surface into small segment, and the area of each segment is represented by delta A. Delta represents a small change in any quantity. Here I am talking about the area, so that should be equal to change in small segment of that closed surface, right. So and this small segment must be a flat surface, and here the electric field must be uniform, and electric field across each segment over the closed surface must be uniform, because each segment of this closed surface is at equal distance with respect to center, where the point charge, where the source charge is located. So therefore, the distance between the point charge which is located at the center of this closed surface and to the surface of this closed surface is constant. So therefore, electric field is constant. So now we are in the position to apply the definition of electric flux, because under this supposition we are able to apply the definition of electric flux, because this supposition satisfies the two conditions. The first condition is that the surface is a flat surface, and the second condition is that electric field is uniform across each segment. So therefore, now we are in the position to apply the definition of electric flux in order to find out the electric flux of the closed surface. So as we have divided the whole closed surface into many segments, right, say delta A1, delta A2, delta A3, delta A4 and so on, we have divided into n segments, and generally the area of each segment is represented by delta A, and the electric field across each segment is equal to E. Now according to the previous definition, the electric flux through one of the segment is equal to, okay, the electric flux across each segment, say delta A, which is equal to E dot dA. Now what should be the electric flux to the entire closed surface? So the electric flux would be across the entire closed surface must be equal to the sum of electric flux through each segment. I mean, we have to add up all the electric flux through each segments, and then we will be able to find out the electric flux to the over the entire closed surface. So therefore, the electric flux to the entire closed surface is equal to sum of E dot dA. Here the symbol, which is, this is called, in Greek word this is called sigma, and this sigma is applicable for summation of any quantities, right? And this sigma is useful only for specific summation. If we have a we have two kinds of summation. One is continuous distribution of an object, and if you would like to add that continuous distribution of an object, where we are using the symbol of integration. And the second things, the things are divided into discrete form, right, having some specific area of each segment of each quantity. So in order to add the discrete quantities, we are using the sigma or summation symbol, and in order to use a very small changing, we are using the symbol of integration. This is the difference between integration and summation. In fact, both have the same output, but in case of sigma, if we have quantities, they are distributed discretely. So to add all these quantities, we are using the symbol of sigma in Greek words, and which is symbolically represented by this symbol, which is present over here, right. So sigma of E dot dA, which is represent the electric flux over the entire closed surface, having point charge at the center of closed surface, right. Okay, so now there are certain things associated with the closed surface. I means we have already discussed that electric flux is a scalar quantity, and you know that scalar quantity is just a number with proper unit. So that number could be positive, that number could be 0, and that number could be negative, right. We have three different possibilities. So on the basis of three different possibilities, I would like to relate these three different possibilities with the electric flux to the closed surface, right. So here in this page with title of Do You Know, we have three figures, figure A, B and C. In each figure we will have a different flux, right. So in first case, the electric flux to the closed surface would be 0. In the second case, the electric flux to the closed surface will be negative, while in the third case, see in figure C, the electric flux to the closed surface will be positive, right. So now the question is that what is the physical meaning of positive flux, zero flux and negative flux. Okay, when I am talking about the zero flux means that the number of field line entering to the closed surface is equal to the number of field line leaving the closed surface. So in that situation, the net flux will be 0, right? Once again, I am going to repeat that flux, basically this is the measurement of the field line across any surface area. So look at that, if the number of field line entering the closed surface is exactly equal to the number of field line leaving the closed surface, then there will be no electric flux across the closed surface, right? So I would like to resemble this thing with some practical situation. Suppose you have a room, right, and that room have two doors, right. So some students, suppose 5 students are entering to the room in one door, and the same number of students are leaving from the room through another door. So now, is there will be any number of students within the room? So the answer is no. There will be no students within the room, because the number of students entering through one door of the room is exactly equal to the number of students leaving the room through another door. So at the end, we will have no student within the room. So net, we have no person. In the same fashion, if we have a closed surface where the number of field line across leaving the surface is equal to the number of field line entering the surface, then the net flux will be 0, right. Okay, so in second case, the electric flux to the closed surface as shown in figure B is negative. Negative means given more number of field line entering the closed surface and less number of field line leaving the closed surface, then in that situation the electric flux will be negative, right. In that situation, the net flux will be negative. So in the third figure as shown in figure C, the electric flux to the closed surface is positive. So look at that, 2 field lines entering to the closed surface and 3 field line leaving the closed surface. So the field line leaving the closed surface is greater than the field line entering the closed surface. So therefore, the net flux should be positive, right. So also remember one thing, from this we concluded that the number of the electric flux entering to the closed surface always to be taken negative, while the electric flux leaving the closed surface to be taken positive, right. So this is important also. Sometimes you have to know about that, what is the actual meaning of negative flux and what is the actual meaning of positive flux and what is the actual meaning of zero flux, right. Okay, so this is what we discussed about the electric flux through the closed surface, and there are different possibilities, right. Okay, the first we will discuss later on why, in which situation the electric flux through the closed surface will be 0, and in which situation the electric flux through the closed surface will be positive, and in which situation the electric flux through the closed surface will be negative. I mean, from this demonstration we can also conclude about the amount of charge enclosed by the closed surface. From this demonstration, given the electric flux is positive, electric flux is negative, electric flux is 0. So this in fact gives information about the amount of charge enclosed by the closed surface, right. So we will relate this concept, how the amount of charge enclosed by the closed surface related to the electric flux, and this topic will be discussed in the coming topic, that is called Gauss's law. So Gauss law relates the amount of charge enclosed by the closed surface with the electric flux to the closed surface, and on the basis of that statement I am able to know about that what is the actual contents of the amount of charge, what is the nature of charge enclosed by the closed surface, right. So let us come to the Gauss law, and we are going to state the Gauss law, and on the basis of that Gauss law we will also, and in the later we will discuss some application of Gauss law as well. Okay, as we have already discussed about the electric flux to the closed surface and general electric flux we have already discussed, and also we have discussed about the source of electric field, which is the charge, right, according from Michael Faraday concept. Now we are in the position to know that how the amount of charge enclosed by the closed surface related with the electric flux through the closed surface. So this concept will be covered in this topic, which is called Gauss's law, and this is also one of the tools for solving the electrostatic problem. I mean ki before Gauss law we have discussed one of the law that is called Coulomb's law, which involve the force between the 2-point charges, right, and force is a vector quantity. And to solve some electrostatic problem by using law is a little bit complicated job. And why it is complicated job? Because Coulomb's law involve a force, and force is a vector quantity, and we know about that. To play with the vector quantity is a little bit complicated job as compared to the scalar quantities. And you will be know about the Gauss law, which relates the electric flux to the closed surface with the amount of charge enclosed by the closed surface, and electric flux is a scalar quantity, not a vector quantity. So therefore, if we have a same electrostatic problem and I would like to solve the same problem by using Gauss law, so it will be more easy to solve the same electrostatic problem by using Gauss law as compared to by using the Coulomb's law. One thing more you have to keep in your mind, Gauss law is a more fundamental law as compared to the Coulomb's law. I mean, I can derive the Coulomb's law from the Gauss law. I can derive the Coulomb's law from the Gauss law, while the reverse is not possible. So therefore, Gauss law is more fundamental equation as compared to than the Coulomb's law. So therefore, Gauss law become one of the equation of electromagnetism. So we have 4 equation of electromagnetism, that is called Maxwell equation. So out of 4 equation, Gauss law is one of the equation, and on the basis of these 4 equation we can deal the whole electrostatic and electrodynamical problems. Okay, anyway, this is a little bit for general knowledge. Of course, this is beyond of your level, but I would like to give you some general concept regarding this Gauss law. So you have to know that Gauss law is one of the alternative method to calculate the electric field of a given charge distribution, relies on theorem that is called Gauss law. So first of all, I am going to state the Gauss law, what is Gauss law in general, and then we will going to derive this statement on the basis of some mathematical steps, right. Okay, so Gauss law state that, so here in the blue statement, in the blue paragraph, which is represent the Gauss statement of the Gauss law. So Gauss law state that the net flux through a closed surface is equal to the total charge enclosed by the surface divided by permittivity of free space. We have already discussed about the permittivity of free space. So in simple words, Gauss law relate the electric flux to the closed surface with the amount of charge enclosed by the closed surface. So now this statement mathematically is equal to the electric flux to the closed surface is equal to the amount of charge enclosed by the surface divided by permittivity of free space, right. So this is what we call Gauss's law. On the basis of this simple statement, I am in the position to solve some electrostatic problem. By electrostatic problem, I mean I can find out the electric field, I can find out the amount of charge enclosed by the closed surface, I can find out the surface charge density, I mean I can find out the volume charge density, etc. Okay, so let me derive this equation, this statement, how to derive this statement. So for this I am going to consider one of the most symmetrical closed surface, which is a sphere, in a form of sphere, right, because sphere is a more symmetrical object. So I can apply any shape closed surface object, but for simplicity, in order to make our mathematical steps easy, I am going to apply one of the more symmetrical object, that is called closed sphere, in a form of spherical object. So consider a sphere having charge inside a sphere located at their center, and the radius of this sphere is represented by small r, as shown in figure A, and represented by blue color. Okay, so now I am going to find out the electric flux to the closed surface. Of course, this is not a flat surface, once again, as we have already discussed in the previous lecture. So we have to make some assumption, we have to make some supposition, and the supposition is that we have to divide the whole closed surface into small segment, and the area of each segment is represented by a small segment that is called delta A, and the electric field across this segment is equal to E, which is also uniform, right. So the division of this sphere into small segment is represented by another figure that is called B, right. So we have to divide this sphere into that kind of segment, and we will find out the electric flux through each segment, and finally we will add all of the flux through the each segment, and this will give us the electric flux through the closed surface. Okay. So here we have to find out the electric flux through the small element delta A, which is equal to pi 1, that is equal to E dot delta A1, which is equal to E1 delta A1 cos of theta. Look at the figure. In this figure, the electric field and vector area is in same direction. So theta is 0. So therefore, cos 0 is 1. So A1 delta A1. This is the electric flux through one of the segment of this closed surface, say delta A1. Similarly, the electric flux through the other small elements, say delta A2, which is equal to E dot D delta A2. Once again, this segment and electric field will be in the same direction. So theta is 0 and cos 0 is 1. So this equation reduced to E2 delta A2. And similarly, for if we have n segments, then the electric flux for n segment should be equal to En dot delta n, and similarly En and delta an is in same direction, so theta is 0. So we have En and delta an. Now electric flux is a is a scalar quantity, so we can add these quantities just on numbers, right. So therefore the electric flux over the entire closed surface is equal to sum of electric flux through each segment. Like the net flux will be equal to flux through segment E1, like pi 1 plus pi 2 plus pi 3 plus pi 4 and plus pi n, right. So once again, this is our discrete segments. So therefore the in term of summation it could be equal to sigma of E dot delta A. So sigma की सबस्क्रिप्ट में हमारे पास क्या surface, I mean कि sum of electric flux over the closed surface of E delta A. Okay, but here the electric field is uniform, it's a constant, so I can write this electric field out of this summation, right. Of course, if it is constant, so no need to add this quantity, so I can write it outside of this sigma. So under that consideration, we have electric flux over the closed surface is equal to E time sigma of over the closed surface is equal to delta A. Okay, so here E is the electric field due to point charge, and this equation we have already derived as well in your previous knowledge, in the previous topic. Electric field due to point charge is simply equal to Q by mu naught Q by 4 phi mu naught time into 1 over r square, right. So this equation we have already derived, Q by 4 pi epsilon naught into 1 over r square. This is the electric field due to point charge, and here also at the center of this closed surface we have a point charge. Okay, so just plugging this equation into the equation of electric flux to the closed surface. So we have this equation for Q by 4 pi epsilon naught time 1 over r square into sigma of delta A. So here sigma of delta A represents the surface of the closed surface of the sphere, which represents the entire surface of the sphere, and we know that the area of the sphere is equal to 4 pi r square, right. This is already famous from geometrical interpretation. From your geometry you must know about that, what should be the area of sphere, what should be the area of you have a different objects, and from their geometry you can calculate their areas, right. So here we have a spherical object, so their surface area, the surface area of any spherical object is simply equal to 4 pi r square. So here sigma of delta A represents the entire surface area of the sphere, so therefore this equivalent to 4 pi r square. So now just replace this sigma of delta A by 4 pi r square. So, we have this equation, this one. So, Q time Q by 4 pi epsilon naught into 1 over r square into 4 pi r square. So, cancelling the same terms, 4 pi r square is in the numerator as well as in the denominator. So, when we cancel all the same terms, so this equation is reduced to Q by epsilon naught, and say equation number 11.13. Now, this is what we call the Gauss law. Now, this mathematical equation simply states that the electric flux to the closed surface is equal to 1 by epsilon naught time the total amount of charge enclosed by the closed surface divided by permittivity of free space. So, the above equation show that the electric flux does not depends upon the shape or geometry of the closed surface, but it depends upon the medium and the charge enclosed by that surface. Look at this equation, there is no factor like r square, like r, like which is related with the geometry of that sphere. So, therefore, this equation clearly demonstrates that the electric flux to the closed surface does not depend upon the shape, whatever shape closed surface you can use, right. So, you would have the same amount of electric flux. Okay, so now this is for the specific for well geometrical shape object closed closed surface, right. Now, the question is that if we consider the irregular shape object, I mean let us suppose if the amount of charge enclosed by the closed surface which have an irregular shape, then what happened to the electric flux? According to this equation, we claim that electric flux does not depend upon the shape of an object, right, which enclose some amount of charge. But now I am going to verify this statement by considering the amount of charge enclosed by the closed surface, and let us see what happened, right. And the same thing will be based on some mathematical steps, and after following some mathematical steps we are going to see that what should be the electric flux through the closed surface enclosed by the object which is not regular object, which have some irregular shape object. Okay. So, we have n charges, say Q1, Q2, Q3 and Qn point charges enclosed by the irregular shaped object, the irregular closed surface, say S. Okay, so once again we have to divide the closed surface into small segments as usual, as we have done in previous cases, and we will find out the electric flux through each charge enclosed by the closed surface. So, let us suppose from previous knowledge the electric flux due to charge Q1 is equal to Q1 by epsilon naught, as we have discussed already, and similarly the electric flux due to another charge, say point charge Q2, will be equal to Q2 by epsilon naught, and similarly the electric flux to another charge should be equal to Q3 by epsilon naught, and so on. Now, the net flux through the irregular surface will be equal to the electric flux due to charge Q1 plus due to charge Q2 plus due to charge Q3 plus due to charge Q3 and so on. So, therefore, the net flux through the irregular surface is equal to Q1 by epsilon naught plus Q2 by epsilon naught plus Q3 by epsilon naught and so on up to n charges. So, epsilon naught is common. So, just take this quantity as a common. So, we have 1 by epsilon naught time Q1 plus Q2 plus Q3 and Qn. So, here this number represents the total amount of charge enclosed by the closed surface. So, simply replace this summation by the net charge enclosed by the closed surface. So, total charge enclosed by the surface is simply equal to represented by capital Q. So, capital Q represents the amount of charge, the net amount of charge enclosed by the closed surface which have no regular shape. So, simply this statement is equivalent to the previous one as we discussed and as we derived, which is equal to 11.13. So, in both equations there is no factor related to the geometry of the closed surface. So, this both equations clearly demonstrate that electric flux through any closed surface is equal to 1 over epsilon naught times to the total charge enclosed by the closed surface, and it does not depends upon any geometrical factor or anything else, right. This is what we call Gauss law. Therefore, Gauss law is to solve some practical problem. I means if you would like to find out the electric field intensity due to various distribution of charges, so that can be solved on the basis of Gauss law easily as compared to the Coulomb's law, right. Okay, so this is enough, I think so, for the today lesson. If there is any complication, there is any confusion regarding any point, regarding any mathematical steps, regarding any qualitatively as well as quantitatively demonstration, so you can communicate with me. I will try my best to solve your problem, right. But please participate in the interaction. This is very important. When you are participating in the interaction with me, then other students may also know well about this topic. When you are not participating in the class, I mean you are not going to ask any questions regarding any steps, then you are not going to broaden your mind, your concept, etc. So therefore, I am requesting to all of you, you must ask the questions, right. Suppose if I am unable to answer at that position, so I will try my best to answer in the next day, etc. But I definitely provide the answer of that question. So this is the end. So tomorrow, I mean in the next lesson we will discuss some of the applications of this Gauss law. I mean how to apply Gauss law in order to find out to solve some electrostatic problems on the basis of Gauss law, right. So I hope you enjoying this video and must highlight some question, and I must expect some question regarding this topic. And see you in the next class via Zoom, where we will discuss about your questions and answers. Thank you very much.